Okay, so we're going to quickly go over measures of fit for multiple regression. This is in lecture notes 6, page 4. So measures of fit in a single variable regression, or a regression model with only one x variable, one right-hand side variable. We had the standard error of regression that we talked about before, and we also had the R squared. We also called this goodness of fit statistics before. Okay, so in multiple regression it's slightly different. The only thing that really changes, we have to account for the fact that we are including more and more regressors, more right-hand side variables, more x variables. So we have a degree of freedom correction that we have to do. So let's start with the standard error of regression. I'll just give you the formula. Standard error of regression is equal to the standard deviation of u hat I with a degree of freedom correction. So the degrees of freedom are the number of regressors you have in your model, essentially. So the regressors, or you could count up the coefficients. So beta 0, beta 1, beta 2, etc. That's how many coefficients you have. This is going to be equal to standard error of regression in multiple regression is going to be equal to the square root of 1 over n minus k minus 1. So before we only had 1 over n minus 1. Now we have this k parameter, which is the number of regressors you have in your model, times the sum of I equals 1 to n of u hat I squared. So this is exactly the same as it was before, except for this minus k. That's your degree of freedom correction. So the u hat I is exactly the same. The u hat I, let's just define it. We have actual equals predicted, so the predicted values plus the residual. And so what is the actual? The actual is the yi, the predicted is the y hat I, and the residual is the u hat I. So we're taking those residuals, the u hat i's, and we're squaring them, summing them up, and then multiplying by 1 over n minus k minus 1, taking the square root of all of that. So it's the standard deviation of the u hats. We also have a root mean squared error, which is the standard deviation of ui without the degree of freedom correction. So the root mean squared error, we'll just write this down so that you've seen it. Root mean squared error equals 1 over n times the sum of I equals 1 to n of u hat I squared. We also have the r squared. So the r squared doesn't, well, the r squared changes. So it's the fraction of variance in y explained by x. Fraction of variance of y in y explained by x. Or in this case, because we're dealing with multiple x variables, by x's. By the x's. So the r squared, same as before, it's explained sum of squares over the total sum of squares, or we had 1 minus the residual sum of squares over the total sum of squares, where each of these explain sum of squares, where the explained sum of squares is equal to the sum I equals 1 to n of y hat I minus yi squared. The total sum of squares is equal to the sum of I equals 1 to n of yi minus y bar. Actually, I wrote that wrong up there. Should be y bar. So it's the difference between these two. Maybe I should write this in red. You can see the difference. These are exactly the same, except for one is using the predicted values and one is using the actual values, the yi's. So the difference between either the difference between the predicted values in the mean or the actual values in the mean of the data and squaring all that. And then the explained sum of squares is equal to I equals 1 to n of the u hat I squared. Or, sorry, that should be the residual sum of squares. Okay, so that's what we had before. The problem here is that the r squared increases systematically when you add another regressor. So just by adding an additional regressor to the model, the r squared mechanically goes up. It doesn't necessarily mean that that additional variable actually has predictive power for the y, for predicting the y variable, or explaining the variation in the y variable. It's just a mechanical thing about how the r squared is calculated. So that means we need to account for this, and we do that again using the degree of freedom correction, just like we did in the standard error of regression. We're going to adjust for the fact that we're just adding additional regressors to the model. So we're going to take our r squared and we're going to adjust it for degrees of freedom. We're going to call this the adjusted r squared. This is going to be the adjusted r squared. Or it's an r squared with a degree of freedom correction. And we know, so this is something you should remember, we know the adjusted r squared has to be less than or equal to the regular r squared. So the adjusted r squared with a degree of freedom correction has to be less than or equal to the regular r squared. So it penalizes the regular r squared for including another regressor in the model. So it goes like this. Adjusted r squared equals 1 minus n minus 1 over n minus k minus 1. So there's our degree of freedom correction. Number k is our degree of freedom correction, number of regressors in the model, times the sum of squared residuals, or the residual sum of squares over the total sum of squares. So let's look at a couple of r squared values from our test score and student-teacher ratio example. So let's suppose we have a model, a single variable model, test scores, as a function of student-teacher ratios. And we get an r squared here of 0.05. And we get a standard error of regression of 18.6. Then we add an additional regressor to the model. We're going to add the percent English language learners. So that was the percent of students in the district that are non-native English speakers. The R squared is going to be equal to 0.426. And then the adjusted R squared with a little bar on top, is equal to 0.424. The standard error of regression is equal to 14.5. So let's take a look at a couple of things we can learn from this. Okay, the R squared in the single variable model is only 5%, 0.05. That says that not a whole lot of the variation in test scores is explained by student-teacher ratios. Again, that doesn't mean that student-teacher ratios is not a good variable to have in our model, or it has no predictive power for test scores. It just means that there's a lot of information still left in our error term, our U term, that we haven't drawn here, but we could take the hat off here. We know there's an error here, a U hat I. I can draw U better than that. So there's still a lot of information contained in that error that explains the variation in test scores. Again, it doesn't mean student-teacher ratios is bad, it just means that we're missing a lot of information. If we add % English language learners, the R squared goes up dramatically. It goes up to 42.6%, meaning that we're explaining a lot more of the variation in test scores just by the % of English language learners added to the model. But the thing I want to point out here is that we also have an adjusted R squared, and that adjusted R squared is slightly lower than the regular R squared. So going back to our little rule up here, we know the R squared has to be, the adjusted R squared has to be less than or equal to the regular R squared, and indeed it is. So one could argue that the second model here, if we call this model 2, this one model 1, the second model is maybe a better model because it's explaining more of the variation in test scores. If that's what you're hoping to do, is explain the variation in test scores. We also talked about omitted variable bias, and we know that the coefficient on student-teacher ratios went down when we included % English language learners, so that's another indication that Model 2 is a better model. I mean, we're taking care of some of the omitted variable bias that's in equation 1 there. I'll show you practically how this works in R. So here's the code for problem set 2 or problem set 4. So let's look at we're regressing wages on a series of variables here: education, experience, hours worked, married, a dummy variable for married, dummy variable for female. We can look at that data. Here it is. I know it's a dummy variable because married only takes on 2 values, 0 and 1. Female only takes on 2 values, 0 and 1. So I only gave you, I think in the script I only gave you this much information for your linear model 2. So to add additional variables, so here we have wages regressed on education, experience, and hours worked. To add additional variables, see what variables we have. We've got experience in them all, we've got hours worked now. All we have to do is add them. So CPS data, $ gives us what variable we want, and then tab gives me the list of variables. I'm going to add married, and go to the CPS data, tab it, married, female. How about that? Female. So I should be able to run this. I put my cursor on this line. Let's run. Spits out linear mod 2 has been run. It's a linear model with wages regressed on education, experience, hours worked, married, and female using the CPS data. Now let's summarize linear model 2, and we get this. We get the summary of our regression. So what do we see? Our beta 0 coefficient, our intercept, is equal to negative 14.497 with a standard error of 2.4, a t-statistic of negative 5.9. So remember that our 95% confident rule is going to be that t-statistic has to be greater in absolute value than 1.96. This one is, so that means our p-value is extremely small, 3.91 to the e times 10 to the minus 9, so really small. Coefficient on education, this would be beta 1 because education was the first variable in the model, is 2.095, standard error of 0.13, t-statistic of 15.4, which is really large, so we have a very small p-value again. So we can go down and look at all of our coefficient estimates here, and their standard errors, their t-statistics, and their p-values. But for this little lecture, we're focusing on the r-squared. So the residual standard error, that's the standard error of regression with 994 degrees of freedom. That's going to be the number of n minus k minus 1. So n was 1,000. Should have 1,000. Yeah, 1,000 observations. Minus k, which is going to be 1, 2, 3, 4, 5. 5 for the beta 0. Minus n minus k, so n minus 5 would be 1,000 minus 5, which is 995, minus 1, which is 994 degrees of freedom. Our multiple r squared, so that's just the regular r squared, is 0.2357, and our adjusted r squared is 0.2319. So again, the adjusted r squared is less than the regular r squared. And we'll talk about f statistics in another lecture.